Hey, g'day, it's Presto and thanks for stopping by. Now, it's been a couple of weeks since I published a video, and the reason for that is that my wife and I have just returned from a holiday in New Zealand. Now, we try to get over there regularly. Our son lives and works in Wellington, which is the capital of New Zealand. So we called in to see him, and then we flew across to Queenstown on the South Island, picked up a car and did a road trip around that part of New Zealand. Now, we'd been there in 2004, 2005, but we wanted to see it again, and it was absolutely amazing. So we saw some beautiful places like Milford Sound, went up to Mount Cook, we drove around Central Otago, which is an amazing place to see, and we did a wonderful trip on a vessel called the TS Earnslaw. Now, the Earnslaw is one of the last remaining working steamships in the southern hemisphere, and it's absolutely beautifully maintained. And you can stand up on the top deck of the vessel and look down into the engine room. You can see the engineers operating the two triple expansion condensing steam engines. You can see the stokers feeding the boilers, and you can hear the engine telegraph clanging away. It was amazing. So got the t-shirt to prove it. But today's project is about this little turbojet engine which I built back in 2008, 2009. Now, I got it built. It ran beautifully, and then through my own fault I mismanaged the start cycle and I got a thing called a hot start. Now, in a hot start you've got too much fuel, not enough air velocity, and the rear end of the engine overheated enough to distort an assembly called a nozzle guide vane assembly, and it made the turbine rub. Now, when it's rubbing on that shroud, it just simply won't spin and it won't start. So today's project is to dismantle or partly dismantle the engine, fix that problem, get it running again, and I'll show you hopefully the engine running, and it's scary but also very exciting. But first, I got a new sticker, so let's get that up on the door and we'll talk about the owner. Now, today's sticker was sent to me by Kyle. Now, Kyle lives in Southern California. In 2014 he set up a one-man workshop. He's a welder and fabricator, and he was working on Volkswagen cars, motorcycles, all sorts of fabrication jobs, and he just hung out there with his shop dog and was living his best life. And then it all went bad. Now, in February this year, 1st February this year, an arsonist set fire to his workshop, and basically what wasn't destroyed by the fire was destroyed by smoke and also the water from the fire engines. So when Kyle had a look inside, his milling machine was destroyed, his lathe. I think he's been able to get the lathe back up and running, sort of. But there was also the customer jobs that were in the workshop as well. So here's just a few photos of the destruction that Kyle turned up to see. And it also turns out that his insurance broker didn't really do the right thing by him, and he was unable to use the insurance to pay back his customers. And you think, well, it can't possibly get any worse, and then it did. Kyle's dog died just recently from heart cancer, and he was absolutely devastated, as you would be. So you think, well, that's the end of it, but it's not. So just recently his mother passed away as well. So it sort of makes you question your own position, and I know that if I was to lose my workshop through fire, it would devastate me. A lot of the stuff that I have here is irreplaceable, and you would never get back to a position that you were in. Now, long story short, Kyle's wife set up a GoFundMe page. I'll put a link in the description below. Now, I sent Kyle a small donation on behalf of this channel, but if you'd like to help him out, I'm sure that any donation you can make would be appreciated. Now, it turns out that this sticker here is a representation of his life story so far. So his initials that you see on here are KB. Now, apparently his friends call him Kielbasa, which is the Polish sausage. It's just a bit of a joke about his name. And his shop name was called KBI, Kielbasa Industries. And this little dude in the middle here is the arsonist that set fire to his workshop. So he's riding along the street on his push bike, he's got his lighter in his hand, and here's just a few little items from Kyle's workshop here in the sticker as well. So please help out if you can. We hear these devastating stories from time to time, and if we can help, I think it's the right thing to do. So that's Kyle's story, but let's get back over to the bench and have a look at this engine. So this is the engine now. It's called a Hurricane, and I read an article in this magazine here, the Australian Model Engineer magazine, It's issue number 135, and it was published in November-December 2007. In the magazine I saw this article about building this engine, the Hurricane. It had a cross section of the engine, and I took one look at it and I said, yeah, that's easy, I can make that. I didn't realise how complex it is building an engine of this type. So the machining tolerances on a lot of the parts is between 20 and 50 microns, and there's absolutely no room for sloppy fits or sort of bad fits. But I got it running and it ran beautifully. I actually made a video and put it on YouTube, but it was on a channel that I created, and I can't even remember what the password for that channel is anymore. But it did run, and I was really happy with it. The article in this magazine was written by a gentleman named Neville Robertson. Now, he designed this engine based on the well-known KJ66 model turbojet engine, a commercially made engine. It has a 66mm turbine in the rear and a 70mm impeller for the compressor. It runs on kerosene with two-stroke oil added to it for lubricating the bearings. It must be started on liquid propane gas. Once the gas ignites and the combustion chamber starts to heat up, you can feed in the kerosene, and after that it accelerates away and runs between 100,000 and 125,000 RPM, and it should produce about 10 kilos of thrust. Now, I built the engine not for an aircraft, I just wanted to hear it run. And it was that, that sound of the model turbojet engine that got me sucked into the whole project. Now, today's job is to fix up a number of problems. One of them is that the fuel pump won't run at 0 RPM. So when you turn on the switch for the fuel pump and have the control set to 0, it actually starts to feed fuel straight away, which makes starting very complicated. And also, as I said, the turbine is rubbing on the nozzle guide vane assembly, so that needs to be fixed. Now also, there are two batteries inside this control case here. These are just gel batteries, and they were both dead when I took them out. They've been sitting around for about 10 years. So I've got two new batteries, so we're going to get those hooked up. I'm going to clean everything, get everything sort of looking tidy and neat again. And then, hopefully we can get it to run. You can see I removed the engine from the top of this control box here. This is just a steel fabrication, and I bolt the engine to the top of that. And then inside this I've got the switches and the pressure gauge and the control for the fuel pump. And as you can see, this wiring is an absolute mess. And remember, I did this about 12, 13 years ago, and I can't remember what I was trying to achieve with this. It did actually work, but it's really hard to diagnose what's going on here. So I think I'm going to strip all of that wiring out and do it again, do it properly. But let's have a look at this chassis here. I'll explain three very important parts of making this engine run. Now, there is space inside this chassis here for two of these batteries. Now, these are 6 volt 7 amp hour batteries. I'm going to run two of these in parallel, and that will give me enough power to run all of these auxiliary systems to the engine. Now, in the original design I had these batteries lying on this side. Now, I'm not sure if that's very good for the batteries. I think they need to stay upright. So I'm going to rebuild this chassis and the top cover to give me more height, but less length and less width. So that will be, I think, an improvement to keep these batteries alive for longer. Now, this little gadget here is a glow plug driver, and this takes the 6 volts from the batteries and converts it to 1.5 volts with enough current to run the glow plug. Now, alongside that is a PWM controller for the fuel pump. Now, this is a kit that I bought from an electronics supplier, and I modified it to make it run on 6 volts. However, it's not been very successful. The problem is that you can't regulate the speed down to 0. So even with the potentiometer sat on 0, and if you turn the fuel pump on, it will actually start to pump fuel straight away. So I'm going to replace that with this one here. This is just an off-the-shelf PWM controller I bought on eBay. Now, alongside that is the fuel pump. This is once again an off-the-shelf unit I bought. It's from a company called Flightworks, and it's just an electric fuel pump, and it supplies the kerosene to the engine to keep it running. And unlike full-size engines, you do need electric power to keep this jet engine running. In full-size engines, the fuel pump or the fuel metering system is actually run off the main shaft of the turbine. So once the engine starts, you don't need any electric power to keep it running, but with this little model one here, we need to have power on all of the time. If I switch the main control off, the engine will just stop. Okay, time for a bit of an update. Now, I've spent a couple of days making this new aluminium chassis for the control box. So this is considerably narrower and also shorter in this direction here, but I've made it taller so that I can fit the 2 batteries into that 3D printed battery compartment. Now that keeps the batteries secure, but it also keeps them vertical, and I think that's going to prolong the life of the batteries. In the back here is a charging port. When the charging plug is inserted, it disconnects power from the rest of the systems inside this box here. I've got a distribution block here, so we'll take the negative and positive power and distribute that to the other systems inside. I've mounted the fuel pump permanently now, and I've made some 3D printed fixture plates here for these circuit boards. So this one here is the PWM controller for the fuel pump. This one is for the glow plug driver. Now the next thing I need to do is to weld the steel sides onto this top cover. Now again, this is all new. This is 1.6mm thick galvanized steel sheet. It's already been pre-drilled for everything that goes on the top of that cover there. And these sides here are hot rolled steel. It's just what I had, and they will get welded on like so, both sides. Now before I do that though, I need to be able to drill all of the holes in this fascia plate here. Now this is the original fascia plate that I made a long time ago, 12 years ago, and this is made from laser etched 2-ply plastic. And as you can see, it's all distorted and it started to corrode underneath the top layer there. So I'll make a new one. But before I do that, I want to make sure that I'm drilling all of the holes in this piece of steel here in the correct position. So there's a paper copy of what it will look like, but I want to be able to drill it from the other side. So I've made a flipped version of that, that's sort of reversed, and that will go on the other side, like so. I'll hold that down with some tape and I'll center punch all of those positions and do all the drilling. This big hole here is for the case pressure gauge, and I'll need to do that with a hole saw. And I want to do it on the milling machine so I can clamp it down and use a hole saw, metal cutting hole saw, and do it nice and slow. So I'll get all of that done, and then I'll bring you back and show you the partially welded case, and then it will be powder coated later on. So there's my paper template. Remember, this is flipped so that when we drill from the back side, it'll be correct on the front side. And I've marked all of the centers of all the holes with red guidelines. So for example, with this big hole for the case pressure gauge, I can just center punch. And I'll do the same for all of the others, drill all the holes. I'll drill the holes so the switch is slightly oversized, and they'll actually be held in by the holes in that cover there, and they've got slight flats on top and bottom to keep the switch oriented. So I'll get all this done, I'll drill all the holes, and yeah, we'll do some welding. Okay, I've got all the holes drilled now, or nearly all the holes. I do need to drill a small hole above each one of these positions where the switches go, and that's for an LED that illuminates the switch when it's on. Now at the moment, these holes in the steel are quite a lot bigger than the fittings that go in there. They'll actually be held in place by the laser cut holes in the plastic fascia, and they've got a tighter tolerance and they've got the flats on them to stop the switches from rotating. So I'll get all of that done off camera, and I'm going to weld the sides on this off camera, because quite frankly, you don't want to see me welding. Yeah, it's not my favourite thing to do, and I'm not all that good at it anymore. I used to be, but getting old and having shaking hands and poor eyesight, yeah, that's what happens. So I'll get all of that done and I'll show you later on. Okay, there's the top cover all welded up, and no, I'm not going to show you inside because quite frankly it's embarrassing, but it's structurally sound. That's the most important thing. I'm going to fill the very slight gap on the outer edge there with some JB weld, and then I'll powder coat over that and it'll just look like one solid structure. Just for reference, this is the old cover here, and you see how much longer it is and much wider as well. And I'm not sure why I made it that big. I think I was considering stability and weight, trying to keep this thing anchored to the bench with a 10 kilos of thrust for the engine on top there. But in practice, I always clamp this down anyway. Okay, it's taken about 4 days to get to this point, but all of this lower section of the engine is finished now. I've got a new front panel here. This has been laser cut and laser etched from 2-ply plastic. It had to be condensed a bit to make it fit this smaller case. And I've got all the wiring done inside, and believe me, that was a mission. I'll show you why. I'm not particularly neat at doing this sort of work, but it's all in there, it's all working, I've tested it, it's all good. The only problem was the PWM controller I bought for the fuel pump is unsuitable. It just doesn't work with the motor that I've got in there, the fuel pump motor. So I put the old one back, and I'll just have to deal with the clunky way that it starts. But what we need to do now is get the engine disassembled and fix the nozzle guide assembly in the back. First thing we'll do here is remove the shroud from the back of the engine. So it's held in place with 3 M2 stainless steel socket head screws. And this will expose the nozzle guide vane assembly in the back of the engine. So here's the turbine disc. I'll bring you in for a closer look. So this is the actual turbine disc itself, and this should be a free running fit inside this outer assembly, but at the moment it's sort of rubbing, and yeah, you got to force it around. So there's probably an interference at one location around this outer ring here, and that's what we need to fix. But before we can do that, we need to remove the turbine disc, and we need to remove the front cover from the engine to get at the compressor wheel. That's also got to come off, and then the shaft's got to come out of the engine. So I'll do the front end, and then we'll get these parts out of the engine, but everything else is going to be left intact. So the combustion chamber, all the bearing supports and so on, all of that's going to stay in the engine, and we're just going to machine this area here. Alright, this whole starter motor assembly and this duct here should just come off now. Oh, help you to take out all the screws, Mark, idiot. Alright, try again. Okay, so that's the entire starter motor assembly. And this curved duct on the inside here has to be a really close fit on the compressor wheel itself. I think there's something like about 0.1 of a millimeter clearance between that curve and the curve on the blades of the compressor wheel. Now I need to remove the nuts at both ends of the main shaft there, but before I do that I need to get some marks on the compressor wheel and the turbine so that I can clock those two components back together again. Now that's really important because both the compressor wheel and the turbine disc have been balanced, and if we don't get that right, then the entire end of the shaft, or both ends of the shaft, will be out of balance with each other. So I'll get the marks on there, and these are both left-hand nuts on the shaft. So we'll get that off, and then we should be able to get to work on machining that tight spot. Now before I dismantle anything, what I've done is I've marked one of the vanes on the compressor wheel, and there's a scribed mark on the diffuser cover as well. So I'll need to line those 2 points up when I reassemble the compressor wheel onto the shaft. Now at the rear, I've marked the turbine disc with an arrow. I've got one of the blades of the turbine itself marked as well with a black Sharpie, and then I've scratched a mark into the edge of the nozzle guide vane assembly. So again, I need to line all that up when I reassemble it. Now, you can see also here where material has been removed from the turbine disc to balance it. Same at the front with the compressor wheel. It's got a lot of material removed on the inside there, and that's why it's so important that I get the compressor wheel and the turbine disc itself clocked to each other. Now, unfortunately, it's not really easy to align the shaft with either of those two assemblies, so the compressor wheel or the turbine blade, but being a smaller diameter, I don't think it's necessary to do that. But we do need to make sure the two bigger mass rotating assemblies are clocked to each other. Alright, now luckily the nut on the turbine disc itself has come loose first. I'm going to have to grip the compressor wheel to get the other nut loose. So let me do that. Might get lucky here. Or not. Alright, just to save my fingers, I've just wrapped a bit of cloth around the blades there because they're mighty sharp. Okay, got it. Okay, now, might be wondering why I'm doing this in a baking tray. Right, the answer is that the bearings used in this engine are an angular contact bearing. They're a hybrid ceramic steel bearing, and they have what's called crowded races. That means that the balls are just simply fitted into the inner and outer race without anything to separate them. And they've got an alarming habit of completely dismantling themselves. And if you lose one of those little silicon nitride balls, you're up for a new bearing. So I'm going to do this in this big tray here, and if anything falls apart I can capture the bearings, put them back together again. Now, I've done this before. It's really frustrating to do, and I'd rather that they didn't dismantle themselves, but that's very likely. So there's our compressor wheel off, and you can see how much material has been removed at the back of that to get it balanced. Alright, that was quite the mission, but I got that out, and so far the bearings are intact, so that's a good thing, but I still need to get the shaft out. Okay, the front bearing is loose. So you can see the front bearings come out of its housing. Now if I pull on that outer race there, it's going to stay intact, I believe. Yes. Right, so we got that one out. I'm just going to stand that upright. So that's a spacer. Alright, so the shaft comes out. So that's the shaft, and there is a wave washer there which puts the preload on the bearing, so I've got to be careful not to lose that. Alright, now in the notes, Neville Robertson wrote on this, he said you can machine the inner face of the nozzle guide vane with that bearing intact, but it's risky. You've got to put a tailstock centre in the centre of the bearing to support the rear end of the case. What he suggests to do is to take that bearing out and just fit a regular ball bearing in its place. This is the procedure I've come up to machine the inside of the nozzle guide vane assembly. So what I'm going to do at this end is I've taped up the inside of the bearing housing, so if anything happens to this bearing, if anything comes loose, everything will be captured inside that bearing housing. Now I've also set up the flexi chuck and the lathe here, and I've machined a register which is an accurate fit on that bore in the diffuser cover. So with that in place, that will drive this end of the engine accurately. Now at the other end, I've machined up this little aluminium disc. Is relieved in the center, so when I put that in place it won't put any pressure on the inner race of the bearing. So it's basically pressing on the outer race, and that once again it sort of protects the bearing, stops anything coming loose. Now I've got an accurate center there, so I can put this over the flexi chuck very carefully because I don't want to damage anything, and then we can support this with the tailstock center. Alright, so that can now rotate in the lathe. I'll get this little tiny solid carbide boring bar inside there. Now I'm going to show you a little bit of this, but then I'm going to turn the camera off because I really need to concentrate. If I do anything wrong here, I'm going to destroy this end of the engine, and we don't want that. Just been rotating everything by hand here, and I've marked the position at the end of the cut on the DRO, so I'm just going to approach 0 in Z. It's very hard to see what I'm doing here. And then we're just going to clean up this inside surface. Now I don't know if you can see, but the outer ring of the nozzle guide vane assembly is not rotating accurately, but that doesn't really matter. What's important is that the cut that we're about to make is absolutely concentric with the center of the bearing. So if we get that right, the turbine will spin inside that housing there. And I'm just going to clean it up until there are no more high spots. Alright, this is scary. Okay, I'm not sure if you can see that, but I've removed a lot of high spots off there now. It's not fully machined on the inside there, but we don't need it to be. We're just removing any of the distortion that was preventing the turbine from rotating. And we want to keep the gap at the end of the turbine blades and the inner edge of the nozzle guide vane assembly as small as possible. The bigger you have that gap, the more gas can bypass the turbine and therefore not do any work. So I'm just going to go a little bit further and then we'll get it all reassembled. Okay, stopping there. See the bright area that's been machined. There's still some areas that are untouched, but I think that's all we need. Got all that back together again, and no bearings were harmed in the process, which was a huge relief. So I'm going to get this reassembled now. I'll put it on the base, and I guess we need to give it a run. Alright, well it's 12:30. I've been procrastinating all morning, putting this off, and the reason is this is a very scary operation and anything can go wrong. Essentially you've got a spinning fireball of red hot gas constrained inside this very flimsy container, and you've got a hole at either end. I mean, what could possibly go wrong? Now I'm going to have two cameras running. I'll have one on the back end of the engine, and I'll have one so that you can see what I'm doing on the control panel, and I'll put up on the screen what's happening during the start sequence and the run sequence. And then the shutdown is basically just to switch off the fuel pump, and then we're going to run the starter motor just to cool the engine slightly. When you see what happens at the start, you'll see a lot of fire coming out the back of the engine, which is allegedly normal, and you may also see that the stainless steel tail cone gets red hot. Well, that went pretty good actually. It got a bit exciting at the start there, and typically for this type of engine, when you're accelerating after you've actually turned off the starter motor, you tend to get a lot of heat at the back of the engine. You would have noticed from the other camera viewpoint how hot that tail cone was getting. But it is stainless steel, it can sort of withstand that sort of temperature at red heat. But the most critical thing is to make sure you don't distort that nozzle guide vane assembly. But it's still spinning, so I think that's all good. You would have also noticed how I used that entire 1 litre of fuel in about 2.5 minutes, and that's typical of these engines. They are incredibly thirsty. So if this was in a flying model, you get a flight time of around about 2 minutes and you get to land and refuel. Now the other thing is that in all the excitement I forgot to turn off the liquid propane gas. So at the end of the run you shut off the fuel supply, and then you can restart the starter motor, and that keeps the engine spinning and allows it to cool down. And it wasn't until I turned off the starter motor that I heard the gas was still running in the engine. Now in reality it doesn't really hurt it, it just means you've got 2 fuel supplies. Probably makes the engine run a bit better than it would normally, but certainly doesn't hurt anything. You would have noticed that the case pressure was running at about 15 pounds per square inch, so it does actually pressurize the entire engine during that run. And that's actually not hot at all. You can put your hand on that while the engine's running, because there's so much airflow through the engine that it keeps that cool. Now, I think we need to go inside and wind up this video. Yeah, I'm calling that a success. Well, that's it guys. Thank you very much for watching today. I hope you enjoyed that. I just went upstairs and watched the video back again, and I was appalled at how badly my hand was shaking on that throttle. And that's because it's quite a stressful engine to run. It can go catastrophic very quickly, and you just got to be on your toes all the time. If you mismanage that throttle, you can get too much fuel flow, not enough airflow, and it can all go really badly wrong at the back end there. But I just checked it, and it's still spinning over, so that's a good thing. And the sad reality is that this will just get cleaned off now and probably put away in a cupboard, and I won't run it again. But it's nice to know that it can be run. I just have to fill it up with fuel and switch it on and it should go. Now, I've got a couple of really interesting videos coming up again shortly. I want to get back on a regular schedule of posting about every week or 2 weeks. And I've got a metal finishing video coming up after this one, and after that it's going to be something totally different. So tune in for that. But for now, it's Presso signing out. I'll see you next time. Cheers.